Okay, and with that, I'd like to welcome the next two speakers, Falk from IID and Willem from Eclipse provider. And we now move on to the world of the Dataspace, because as you know, we also have a Dataspace watchdog, and I'm very curious to hear about how do you build a data and service mesh using the Dataspace.
Great one. Maybe in the meantime, he's preparing the presentation. I'd like to introduce ourselves. So, my name is Falk. I'm from IV, and he's from University of Applied Sciences, the correct English word, in Mittweida, as a researcher. And our talk today, last talk of today, hopefully you have drink enough coffee. Is that the last one? Oh, good. Is about SDV engineering, and we try to bridge the gap between engineering, software development, and data spaces. And I will try to give you the story why we should do this, and Wilhelm will explain you how data spaces works in detail, more technical, and give you an example. First, a question to the audience. I think most of you are software developers, right? And who of you have ever created the perfect software with a yeah, with a clean architecture and a very clean implementation? Yeah, one yes, everyone has created the perfect software. Maybe
Right, all your
maybe you created a proof of concept MVP or something like this. Then it's perfect. But you will observe it take some iterations, 10 iterations, 20 iterations, asking customers, asking users, seeing the feedback of them, testing a lot, simulation a lot, and after 10 or 20 iterations, you will have a feature or a software which is doing the things that you like at the end. Yeah, 10 or 20 iterations. Maybe, unfortunately, a few months later, other guy or other girl will, impressed by your implementation, make a next step with the ideas you have and give a better software. That's one thing. And the other thing that I came to our problem is, imagine if you have this 10 or 20 iterations in an ecosystems where you're a subcontractor or where you're working with 10 or 20 other parties, where you get feedback from a test weeks or months later, or feedback from the users weeks or months later. And then imagine how much time it will take that you come from the MVP to a feature that is working properly at the user. And that is our daily business when we creating software for vehicles. And that is our talk about. So okay. So I interpret the SDV problem a little bit different, maybe. And we say, okay, what we like to have continuously new features to the customer. That is at the end the goal for all this stuff we do here, and it's all important. Yes, that's the end the goal. And so yes, we do need new hardware and new software architectures. But is this the key to be I hear the word Chinese piece. Chinese speed. Do not use this to be to have these goal features passed to the customer. And maybe I think we do forget a little bit about the engineering process overall we have to create features. I do not speak about software only. We have to create features that create value to the customer. And so you see this picture, we are working today with very old processes in our companies, maybe, and it's very difficult if many companies have to interact. So I like these SDV levels. And the last SDV level, maybe it's the fifth one or sixth one or seventh one, is every time something like an innovation platform. No? Today, I do nothing here about innovation platform, only less things about innovation platforms. But here is, so we have diverse software providers, third-party applications, something like this. We have to have, and we have to have an innovation platform which is able to, or which enables us to have this goal to have features fast as customer. That is SDV level 5, right? That we have to achieve. And then if I have a look at the SDV stack, so several stacks looking like this. So we have hardware abstraction layers, we have some middleware for the IoT edge device, which is the vehicle, middleware for the cloud applications to create APIs to be faster in development, the applications, the apps for the edge device, for the vehicle, and create faster the apps for the cloud. That's the idea we have, what I observe if I look at the SDV activity the most. Then at the beside one, we have tools supporting us. With this innovation platform, it's based on customer experiences? Maybe not. So I have 4 things we have to keep in mind if we're speaking about innovation platforms. These are only 3, I know. First one is what we need to have is something like DevOps approach. DevOps means creating feature, roll out to customer, see what happens. But we are building vehicles, and normal DevOps is between 5 and 10% rollback because of failures in the software. So it's not feasible. So then we have to have a DevOps with a strong left shift, means much more testing, significant more testing before we roll out. Second thing is, obviously, we have to enable AI technologies in the development for testing, for writing code, for requirements engineering and all this stuff. This is just the need we have to be much faster than we are today. And the third one is, maybe it's a conclusion of the first 2 topics. We have to be data-driven. Data-driven means we have to collect data at the customer, and we have to forward our information that we collect in every development step to the next step. And based on the data we observe in the vehicles, we can create new requirements, we can create new training data, and we can validate the software, right? That are 3 basic topics, and innovation platform for engineering SDVs are important. And I say it's 4. The fourth one is not a technical one, it's more organizational one. So we have a very distributed landscape in engineering companies, or companies that are involved in the engineering process. OEMs, tier ones, development service providers like IBM. And in Europe, we see that a centralistic approach did not work. Remember, some companies are crashing. And so we have to live with this problem. Maybe it's a problem, I'm not sure, but with this fact that it is a distributed ecosystem. And what we like to have a seamless and easy integration of all these partners in the development chain. That needs to be machine readable contracts and self-sovereign identities, which are the companies which are sovereign with their data and their information. So now innovation platform needs to be around the software stack which is in the vehicle, and so I can build every time a new software, putting all in and making a new software and putting out, and making new software, putting out. And this is the task of the innovation platform. And now how looks it, or how does it look like? We see that in the engineering process, in the middle, we have four basic, this is the vertical topics, which I call IP domains. Engineering process steps, that is data analytics, that is digital twin, virtualization, something like new virtualization. This is in the middle, this software architecture, software development. Wow. And at the end, testing validation. Yeah. And the right on the left, we have data acquisitions and software update. And we have to have these all in a chain connected to each other. And what we know is, or what we observe is, that inside the IP domain, the interaction is very good, but the interaction between these IP domains in the chain is at least difficult. And so we have to have some, we call it infrastructure, AI-based infrastructure, which connects these IP domains, fetching the assets from in the chain and reworking it that it could be used in another IP domain. So that's basically what we like to have, what we achieve. So two examples to explain this a little bit in detail. First one is we have to have something like development of feature rollout campaigns where we create a new feature, roll out to customers, and see what happens. That's DevOps, right? But surprisingly, the data owner for this process is a driver, and the OEM is only the data provider. And we as the engineering company are the data consumer that are getting only the data we requested. And the data owner, the driver, has to be sure that the information he is sharing is only be used for the purposes he has agreed. And this is very difficult. So we need something, we need a data governance to ensure this over the whole development chain. And this is the task of a Dataspace. And there next slide, I hand over to Wilhelm. So we say, okay, we need to set up this development chain easily with many partners and exchanging information, assets, services, very easy by, we call it data product usage contracts described by ODRL, and the explanation of the properties of the companies are described by verifiable credentials. Now I like to hand over, and he's explaining you a bit about what we experiment and how such a workflow could look like.
Yeah, thank you, Falk. Let's go one step back. Just remember, Falk explained something about a distributed landscape or ecosystem. So this is one, just a lot of participants in this ecosystem with their own applications, with their own business applications, with their own data storages, their own compute power, and all what they want is to communicate, share data, share services, and let's call this distributed landscape a data space. And what we want to do now is just looking inside a communication between two of these participants. So this communication is enabled via the EDC connector, the Eclipse Dataspace Components connector. So, and here we have two sides, the provider side and the consumer side. The provider, that's what the word says, wants to provide this data or this service, and the consumer wants to consume this data for the service or the data space. Both participants have an EDC connector with a control plane which handles all the management, and the data plane which is then for the real transfer of the data which will be used then. Slides have a business application just with an interface or any other service, and this data storage. For the provider, it's the data source, and for the consumer, it's the data sink where the data gets transferred to. So first things that happens when somebody wants to provide this data, he creates an asset. An asset is just a description of the data. What means this data that has to be transferred, what describes this data. Then the provider creates a policy. There are mainly two things that a policy can describe. One is the access policy. So who can see this offer in the data space? Are there any requirements or any obligations that prevent something from seeing this offer? And then at least there has to be a contract created in the connector, and this contract bundles the asset and the two policies, the access and the usage policy. If we have a contract, the offer of the data is accessible in the data space. So the consumer can just see this offer by querying the catalog of the control plane of the EDC connector. And if the contract offer fits for the consumer, he can just sign this contract and then contract negotiation happens. If the contract agreement is set, then the transfer can be started by the consumer. So the control plane signals to the data plane that the transfer can be started, and then the data plane queries the data from its data source and then pushes the data to the data plane of the consumer, and the data plane of the consumer just stores the data in the data sink. Another option for the data transfer is not just copying data from one side to the other side. The other variant is just that the data plane works like a proxy gateway for HTTP requests. So now we have a fully complete data transfer over the data space between two individual data space participants. And when we understand this now, I can add something more complexity to this. So what we don't discuss now about is the other services that take place in a data space. So we have some called core services. These are just for identification in the data space, for registration, for service discovery, so that everybody knows each other in this data space. So let's going back to the other example that I want to show you. Just this complete AI loop, this complete MLOps platform. And on the top, we have a robot. This robot just drives around and records some data from the environment. Then this robot sends its measurement to a data selector. There are this data selector selects just some images, and in the next step, these images has to be annotated. These annotations will be grouped together, and a dataset is created. This dataset, together with a configuration, will be sent to a training cluster, and based on this training configuration in the dataset, a new AI model is trained and deployed to the robot. And then this loop continues being run and run and run again, and the robot will become better and better. So this is the whole idea of the MLOps platform. In the reality, we have not a direct communication between these stages. There is one central AI backend which handles all this. So what we want to do is not having one central backend. We want a data space. Each step just has to be communicated over its data space, has to provide its data, and then the data has to be consumed in the next step. Every participant needs his own connector. and then the communication can happen and the data transfer can be started. So every participant has also the control over his data, can set policies how this data can be used, and also new participants can be added to this circle. So we make it a bit easier by implementing this AI loop, and we grouped some participants together. So we have just for the robot fleet, a data annotator that annotates the data collected by the robot, then an AI configurator, the technical details of the AI model, and then the training platform that trains the AI models and then deploys it back on the robot. So the whole idea behind the Dataspace is we do not have only this participants, we can add also more individual participants to the Dataspace. For example, a second data annotator or a second training platform. And now I want to introduce you to the complete Dataspace-based workflow. I already said something about this. So in the first step, the data provides this measurement in the Dataspace, creates an asset description and policies and the contract for this. And then in the next step, these measurements are consumed, annotated, and then provided as a data set. Additionally, there is a training configuration created, also again with an asset description and a description which datasets will be used for the training in the compute cluster. And also we have here the training cluster, which provides a compute job. And if the compute job is consumed over the Dataspace, then the training cluster consumes the dataset over the Dataspace, the configuration for the AI model, and begins this training. If the training is finished, then the training cluster provides the trained weights, the trained models, again in the Dataspace as an asset. And now I want to give you an insight about this little detail in the workflow. So how a compute job is described, just to give you an example how such something can look like. So for a compute job, we need a data set. So the data on which the training should happen, a configuration about the model, which AI model is which we want to use for the training, and the compute job, which is going to be consumed on the left side. So the Dataspace just has an ID and type and analyse and some properties, maybe just which data is in this data set. It can also have some versions, numbers, and then data address. The data address is just a pointer to the data, so the data plane knows where to find the data which will need to transfer it. Then on the right side, we have the configuration for the training. Also just again an ID and file name, creator, and a sort of properties. Also a data address again. And at the bottom of the page, we have the compute job. It also contains some properties and a data address. And here maybe it's interesting for you. In the properties, there's described which assets the compute job will consume over the Dataspace. So the compute job and data asset with specific ID, and also a configuration asset with specific ID. So this was the first step, creating an asset description, and the next step will then creating a policy. And this policy is described with the ODRL language, the Open Digital Rights language, and here an example for the training configuration. And yeah, maybe this is not very good readable for humans. So IAV created a policy manager where this can just be clicked in a very simple UI, which I want to show you. So you enter here the policy name again. I called it config access and give it the type set. because I want to describe the data set. And then I can add some rules under which permissions this data set can be consumed over the data space. So this is a rule for the usage of the data set, and yeah, it describes that that this asset can only be used with a training configuration. And I also add another constraint here that says that my membership in the data space should be active. And I also can add another constraint, for example, that this data set is for a compute shop. And then this ODRL is created on the right side in the policy manager. And I can use it in the data space to describe my access and usage policies. So I also can add a lot of other constraints. The policy manager helps me with this. There are also buttons that describes all these properties more. So yeah, that's all from my side. And now I want to hand back to Falk again.
No, only a few words. As a conclusion, so where we come from, so we are a development service company at IV. We have dashboards and applications and databases, and we like to have something that people are working on. And as we demonstrated, we using Dataspace technology to have isolated self-sovereign identities that can exchange information, services, and data on a very technical, regulated way. And so we have a distributed ecosystem based on data spaces where we can easily access or construct new development chains. And at IV, we call it a data-driven company, where we enable data spaces inside IV, and we think that this technology could also solve some of the interaction problems if many companies working together to solve a problem. Like Wilhelm is demonstrating with a AI MLOps approach, but the approach could be feasible for any other problems dealing with observations, creating software, and testing software. So, thank you very much. Actually.
Thank you very much. Actually, at some point, we had a blueprint that was trying to get that was extracting driver behavior from the vehicle, sending it via the Dataspace connector to a trusted authority to basically then interface with insurance organizations. So there could be some synergies with it. So, yeah.
Maybe, yeah.
Any questions? Yes.
Thank you very much. I was wondering if there is any way to formally define the data format that you offer as an asset. I mean, it's one thing to say, I have interesting data, but nobody knows what that is.
Data format, yes. That is an important question, but data format is not answered by databases and Eclipse database components. It's only about data exchange. What they do have, they have an asset description. So there are some meta information available about the data.
But that's basically free form or what?
It is basically free-formed. This is what I mean, that we have these vertical IP domains. These vertical IP domains, they have a very good understanding about data formats. And for us, it's very difficult to exchange information between these vertical IP domains because every understand different things in different data formats. That is really difficult. 5 years ago, I would say, okay, yes, API first and define all the APIs, and then we have data formats. but it's too large, too big, too many things to define static data formats. In my opinion, maybe we could use AI agent that interpret the data format from one IP domain and translate it to a data format from another IP domain, because all IP domains have very well structured information about their ontology. And then maybe it would be possible to translate between the different ontologies between the IP domains. That is my long answer to this question, because I think a general one-fits-all data format is not possible at all.
Yeah.
With my check.
Another question. It looked like it would be a peer-to-peer exchange between a provider and a consumer, but still there were some core services that I guess need to be operated by a trusted agent in the middle somewhere. Or who is running these services?
Yes. They call this federated services or something like this. Maybe you have heard about Gaia X. And there is some ecosystem about or container where they have trusted parties, and this is operating these common use services.
But they do this for this particular use case, Container X.
Yes, you could.
So
you
do you
could
need to set
establish
this up?
data spaces, micro data spaces for every problem you like to solve. Or you could establish large data spaces like Container X's.
Yeah, sure. But then you need to find somebody in the middle to operate these core services, right? You always need to do that. Or if they're a generic provider of these core services,
you have to find
some register your data space.
Yes. Yes, you're right. You have to, or the community could have someone. Data spaces are designed that at least one could have this service, but every time more than one is able to provide such kind of service. That is the thinking of, we don't have this one that is ruling all others. Then many companies or many entities could operate these central services. So there could be many in parallel.
The only thing I was thinking, the problem I see is, my understanding is the consumer does a search in the registry of interesting offers. Where do I put my query?
No, the registry is something like distributed registry. So it's not the central registry. So maybe it's a very deep technical question, but everything is distributed. And the only thing that is central is to find the other parties to communicate with, and to have an idea are the other parties are the right parties that I talk with. So identification. That is the role of these central topics. Identification and discovery of the other parties. Not more. All other is bilateral.
First of all, thank you for this great talk and principles you have communicated and presented. I have a question to this example with the data-driven approach to deploy the new AI model to the robot, like you have shown. Did you also consider to implement some maybe feedback loop in that? Because normally in these days you don't just train a model and deploy it and hope that it's better or test it in the lab that it's better. You have something like, we deploy it directly on the target and we swap only to the new model if it's really better in the outside world, because you leave then the well-defined constraints in the testing lab and all that stuff you do. If you want to see if it's really better, then go to the field where is the most variations in data and see if it generalizes very well. And that's the outside world, that's the road.
Yes.
And some OEMs are doing that, not name them, yeah, because that would also have some communication, which is also data-driven, which is back, is it really better? Do we have to swap and all that stuff? Maybe need also some policies on top. Just as an additional hint, maybe you can consider this in the future or have already. Just a few questions.
The project was not about, or the example was not about to have the best MLOps ever. It was only to demonstrate how we could put it to a data space. And yes, for sure, there is some validation and this stuff that we do not just learn a new one and roll out. So we have to be sure that the model is working better than the oldest one.
But the concept would allow that to to extend it.
Yes, but it's a completely different topic. It's more about ML learning of models and evaluating learning. It's not about data spaces.
Thanks, first of all, for the talk and also especially this overview of the sequence diagram that you need to establish the EDC connector. Looking at this number of errors and also these different ways you could exchange and search for the data space and the queries, do you have any insights in the performance that you need to do that? Like how much of latency is added for each data space exchange? Also looking at the question in the chat, where they're asking for real-time performance. I'm not asking about real-time, but generally I'm a bit concerned that it takes quite some time.
Especially these EDC connectors are not designed to run on embedded hardware. These are Java applications that are made to run on a Kubernetes cluster or server.
Sure. Let's say I have a Kafka queue or something running. You would not replace this with an EDC data connection or something like that.
The problem is not the direct peer-to-peer data transfer, because this is handled by the data plane and could also be replaced by, let's say, an Kafka data plane. The problem here is creating the asset, the policy, the contract definition, and then doing this contract decrypt.
That's one thing only, isn't it?
Yeah, this is just one time. This needs a bit time, 2-3 seconds, I would say. Then the data transfer is just copying bits from one side to the other.
But in addition to your question, yes, it's a distributed system where we exchange this information about the available assets to many parties, and it would be expensive. In Catena, for example, they are using the digital twin registry or distributed digital twin registry to make this process a little bit more performant. Because I'm not sure if you're familiar with a digital twin registry, but this have some techniques that are equivalent to the problem, and in Catena they're using these to overcome the problem of have many parties with really many assets, and to find and to identify the asset I like to have.
Second.
Okay. So thank you again.